you'll be able to watch it again. Maybe I'm on now. Okay, good. So, hello, welcome to another Computer Musing. This is the Halloween version. I'm going to have another Christmas lecture in December, be the next one. And topic today is Platologic computing, which I figured if I use a word that nobody knows, somebody has to come and hear the talk, right? So I will at least explain to you, but before you leave, you will know what that means. In fact, it's something that I'm right now writing part of Volume 4 of the Art of Computer Programming, which is kind of the part that I've been waiting longest for. So, for so many years, I've been collecting material for section, which is now called section 7.1.3, and now at last I can put it into into a computer file, and pretty soon it's going to be out there for everybody to read. And sort of this is the, I've enjoyed writing the rest of the book, but this part is the part that really I like the most somehow, and so I hope other people like it too. I got a start on it, but I haven't, and so it's section 7.3 is called Bitwise Tricks and Techniques. My friend Mike Patterson has his own name for this. He calls it BT&T. Which is sort of a sequel to AT&T. But anyway, this will be on the web, available for downloading in a month or so. I'm still in the midst of writing it. If a few people have actually guessed the URL and found it, the rough draft, but I unless you have a lot of time, there's so much other stuff you can do. There's no point in reading it until I've got the ready for beta testing at least. But anyway, this as I say, I have terrific fun writing this because I've been collecting stuff from the folklore that programmers have been doing for years and years, and rarely does it get into print. Nowadays, there's about a dozen websites that of people that have also done their own collection of these tricks, and so I looked at all those websites. There's some of them, at least one of them was hosted at Stanford by Sean Anderson, and then a book came out 2 or 3 years ago called Hacker's Delight, which features a lot of these ideas. And there are errata to that book on the web, so and the author of that book we're in constant touch, so we're trading ideas. These are things that at first we thought they were just tricks, but the difference between a trick and a technique is that a technique is a trick that you can use at least twice. And so once you find 2 different applications for something, then it becomes a technique, and we're understanding more and more about it, and it might even be that we're just seeing the tip of the iceberg, that there's many more of these things. So my general feeling is that right now computer scientists are about somewhat in a state analogous to the way at the end of the 60s we were with respect to data structures. During the first part of the 60s, people were learning about data structures, but the general idea was, well, if you want to use anything more than a linear list, or a vector or a matrix, then you use somebody's package. You use say Lisp or something where somebody has given you a whole bunch of high-level data structures. But all of a sudden, programmers found out that actually they could do their own data structure. It was pretty easy to use to make stacks themselves and so on in their own programs. And so now I think it's about the same. We're about at that level with respect to the stuff I'm talking about today. That it's time to go mainstream with these ideas that they're now understandable enough. We don't have to go to some special compiler that knows how to do some fancy things, but we can actually understand certain methods and use them in our own programs with ease and understanding. And so I'm hoping that this this change, that in other words, these aren't going to, a lot of the things I'm going to be talking about today are going to seem exotic, but I'm hoping that in 10 years, it won't be taught necessarily in first grade, but maybe every programmer will sort of consider that part of their basic toolkit. Now, so what does it mean bitwise? Well, it's just that since the very beginning, computers have had not only the ability to add, subtract, multiply, and divide, but they also had the ability to do what we used to call logical and, but they had other names. So you could take two binary numbers. Unless you had a decimal computer, you could take two binary numbers, and you could take the and of the two things. So you're just getting a one where both of the in the positions where both of the numbers were one. And you also had or, and you had exclusive or, which is in fact at one point was a classified thing. I went to the it was used so often in code breaking. I went to a conference in Los Alamos in 1976 where somebody wrote the truth table for exclusive OR on the blackboard, and the security man erased it immediately. Anyway, it's we can't keep it a secret any longer. So now okay. So for exclusive OR. I write it as a plus in a circle. This means that this means that I take the bits. So let's suppose x is equal to 5, right? And put it in binary as 101, and y is equal to, well, choose a number, not too big. 7. All right. That's lucky. So now. So exclusive OR y, you just take each bit 1 plus 1, but you add it mod 2, so you get 0, 1, 0. Okay, so x o plus y is 2. All right. Then you also have x and y, and I use C notation for this. It's ampersand. So this means you take the and of all the bits, and what do you get? X and y. What? 5. Okay. And x or y is 7. All right, what's x and y bar? That's the complement of y. 0, yeah. And so on. Any Boolean operation that we do. Now we also have like left shift, okay? X left shift 2 would be 101, and we bring in zeros. And so this is a 2, and so this is 20, and x right shift 2 is 1. Okay, so these are the basic bitwise operations that we now. However, let me go to something a little bit harder. Let's try minus x. I'm going to consider that these are integers, but they're infinite precision integers. So minus 1 is going to be all ones. Proceeding out indefinitely. What is minus 5? Anybody know? It's going to have a whole bunch of ones at the beginning. It's minus 5, but what does it look like in binary? It looks like that. Because if we add 5 to that, we can check it. Add 5, where you get 1 and 1 is 2, carry 1. We do carry when we add, not when we do exclusive OR. 1 and 1 is 2. Okay, there we go, and we get it. In general, in fact, if x is any, let's suppose x is equal to alpha and 1 and a whole bunch of zeros, then minus x is equal to alpha bar and 1 and a whole bunch of zeros. This is the complement of alpha, bitwise complement. I should have also mentioned complement. Yeah, okay. So because you add these together and you get 0, and then you get 1 and 1 is 2, and then here we're getting 0 and 1 or 1 and 0 everywhere along. So we're getting 0 all the way around. So this is the formula for minus x. Now, and now I consider that this is a new. These operations are defined on all the integers, and that they're like these are associative operations, exclusive OR, and not this bitwise AND, the bitwise OR, and exclusive OR. They're all associative operations. We can mix them with plus and minus, and imagine that we teach this to everybody. I mean, and we have a whole system that we go beyond ordinary arithmetic and just have a richer collection of things to do. And so you start looking at this, and mathematicians have found a small number of uses of this exclusive OR operation, but they never studied the bitwise AND and bitwise OR. But there's some nice theories about exclusive OR that are used, especially in the theory of games. But also there are interesting identities. In fact, for example, x plus 2 exclusive OR 3 minus 2 is equal to x minus 2 exclusive OR 3 plus 2. Now, that's not obvious, but it just happens to be true. And it's an open problem, actually, to take to solve if somebody writes down a formula involving plus, minus, and exclusive OR to tell you whether it's an identity for all integers. But certain classes of the problem are known. Now, let's check this out just to make sure. So I'll make a table of x here, and say we go 0, 1, 2, 3. I claim it's true for all integers, egg. So I'll write x plus 2 here, and then I will exclusive OR with 3. Okay, well, you can, I'm going to go negative 2, why not? So 0 plus 2 is 2, 3, 4. We can add 2. I don't think we'll have much problem with that. Minus 2 plus 2, minus 1 plus 2. So we get this. Now we get a 2 exclusive OR with 3. So what happens? 0 exclusive OR 3 is 3. 1 exclusive OR 3 is 2, 1, 0. And then 4 exclusive OR 3 is 7, 6, 5, going like this. Minus 1 exclusive OR 3. What was it? Remember, minus 1 is all 1, so exclusive OR 3, it's a whole bunch of 1s followed by 2 2s, minus 4. Okay, now let's also take x minus 2 and exclusive OR 3 with that. So x minus 2 is your minus 5, minus 4, minus 3, minus 2, minus 1, 0, 1, 2, for example. Now we exclusive OR that with 3. And we already have these answers. In fact, we can see what's going on here. So exclusive OR 3, here we get 3. And then here we had a minus 4. Minus 2 exclusive OR 3. Well, it's got to be one bigger, so it's got to be minus 3, minus 2, minus 1. And then this will be minus 8. We had minus 5 a minute ago. It's this guy. So we take exclusive OR 3. It ends with 3 zeros. So minus 8. Okay. And 1 exclusive OR 3 is 2. Okay. So now, if you look at these numbers, they're just 4 apart. And so you can see that if I put this over here, I get a plus 4 over here. So this is indeed a curious identity involving these things. But there are other identities. I haven't thrown in bitwise AND and OR and things like this. And we enrich mathematics, we might as well learn about this system, but very few people have ever studied. Yeah.
When you say that testing identities like this is open, do you mean it's not known whether it's computable, or it's not known whether it's polynomial or linear, or?
Actually, I'm not sure what's not known. Let's see. It was John Conway who told me this once at lunch. But and I don't have all the pages here. Let's see. Here, I've got a level 46 research problem which you can look at. Can we get this on? Oh, okay. This guy here. Incidentally, this is an example of an interesting graphic where you just plot the x squared y and shift right 11, and you get this very interesting pattern. And one of the exercises is to explain why you get these whirls. Anyway, okay, so the results of exercise 15 make it possible to decide whether or not any two given animating functions are equal. Animating functions are functions that alternate plus and exclusive order with constants. And there's a normal form for that, and you can do it. Is there an algorithm that decides whether any given expression is identically zero when expression is constructed from a finite number of integer variables and constants using only the binary? So this is a decision problem. So it's actually whether it's unsolvable or solvable is open, I believe. Yeah. And I got this from John Conway, who was the person who solved the animating function problem. He calls them animating for his own reasons, so it has to do with the game of Nim. Okay, so now these operations get more important because nowadays when 64-bit computers are very common, so we have more bits. If we had only 8-bit registers, then it wouldn't be that interesting to do bitwise operations, because you could do them bit by bit without that much difference. But when we can do 64 bits at a time, we're getting a factor of 64, and that's nothing to sneeze at. So people are now starting to look at what we can do with these operations on bigger and bigger numbers. And so before I get further, my plan today is to show you a whole bunch of really cool hacks, and some of which are tricks and some of which are techniques. Most of which are techniques, and then you can learn the whole thing later at your leisure if you're interested. But when I started seeing how many there are, and then week after week learning yet more amazing things that are possible with these operations, I thought, oh boy, there ought to be a name for this kind of study. And there was one name in the literature, but I don't even want to write it down because for me it was a non-starter. I can tell you though, if you don't breathe it out of this room, one of my former students, Mike Fredman, wrote a paper with Dan Willard about 15 years ago where they decided that they wanted to call this transdichotomous computing. Okay, I looked it up in Google, and I found that somebody the following year wrote a paper that had transdichotomous in the title. But fortunately, it's died out. The last 13 years, there hasn't been anybody else, or at least the last 10 years, as far as I know, using that word. So I want to have another. But I figured the concept's important enough. I want to have a name for it, and. Also, as I'm going to say later on in this lecture, I think it might have implications for hardware design of new kind of computers in the future. So I also looked there, and one possible thing would be VLDW, because people have designed computers with a very large instruction word, and they call those VLIW machines. But I Googled this, and this is already taken by very large data warehouses. So you can't use that. Okay. So I asked Leo Gibas, my student, who's sitting up here with a sheepish grin, and I said, you know, I want to use Greek roots, and so I don't even remember what word I gave him, but I combined some Greek roots, and I said, how does this sound to you, Leo? And he said it. You know, basically it stinks. But he said Platologic is a winner. Platologic sounds good to a Greek person, and it comes from Greek roots meaning wide and word. Okay, actually Platology, let's say, is the Platology is the study of wide words. Now this has nothing to do with a Greek philosopher whose name some of you might remember hearing. You know, it just happens that his name also comes from this root that means wide. And logos, people know that the Greek come from this. So anyway, this is. But I think the connection with Plato is, you know, I mean, okay, so it's misunderstood, but it actually it's so much easier to remember the word, because you don't have to Platologic. It just sounds like it's a word that ought to have been there for years, and so so anyway. But I've got to say a few words. The downside of it is that Platology is a noun, and Platologic is an adjective, not a noun. So I say Platologic computing. I didn't say, building a computer out of Platologic. It's like syntactic, I could say Platological as well, but it just, extra syllable, I don't usually use syntactical, I say syntactic, and so. And, physical, okay, you got music is a noun, but we have syntax. Anyway, so this is an adjective. And you can also say, an adverb platologically and things like this. Okay. Anyway, it might not fly. If somebody has a better name, you never know. But I feel the concept needs a name, and this is the winner so far that I know. Okay. So that's the reason for the title. Now let me show you some. Now, I think the first person who really began to take the covers off as some of the possibilities for Platologic computing was Bill Gosper, who published a famous sequence of instructions in 1972 in the famous memo, Hack Mem, that came out on February 29th, 1972 at MIT. And Gosper's hack was a sequence of 7 operations that I will write down for you and explain. But what happened is after, in a way, Gosper's hack changed the world, because after we realized that Gosper's hack existed, then all of a sudden we said, well, maybe there's other hacks too like this that we can do things that we never thought we could do with these bitwise operations. So here is Gosper's hack. You start out with a number x, and you set u equal to x and minus x. And then you set v to x plus u. And finally, you set y to v plus v exclusive or x divided by u, or divided by 4u, let's say. In other words, shift right 2. So this is one operation to subtract, another one to take the and. That's 2 operations, 3 operations. Here's 4 operations for the exclusive or, 5 to the plus, and whoops, the division is 6. What? 7. 1, 2, 3, 4, 5, 6, 7. Yeah, shift right 2. So what's going on here? This is 1 operation, 2 operations, 3, 4, 5, 6, and 7. Yeah, 6 is for the division, and 7 is for the shift right 2. So you can also call, here, let me call this v exclusive or x divided by u shift right 2. Okay, 7 operations. Now, I told you a minute ago about how do you get minus x from x. Remember that? And look what happens if you take the and of these two guys. You get 1, and you just get a 1 in the position where x's smallest 1 was, okay? An incredibly useful operation. I think Gosper was the first to notice this. But anyway, I haven't seen anything before 1972 where this particular technique was applied. But so if you want to know the smallest one, that extracts it out there. So let's take a typical example of a number x, and suppose x is equal to, well, see, you already gave me. Let me go through the second row here. Call out ones and zeros.
1.
1.
0.
0.
1.
1.
1.
1.
0.
0.
1.
1. This is too random. We got to. Okay, we got to have non-random. Go ahead. You go. 1. I got to have a few more zeros. All right. That's all right. Anyway, it wasn't completely planned. Now, so this is x. So what's u? Well, u is going to be a 1 sitting here, right? As I told you, because minus x is going to be 0, 0, 1, 0, 1, 0, 0, and 1s all the way around. So this is u. Okay, now what's v? Well, x plus u, it's 1, 0, 1, 1, 1, 0, 0, 0, 0. Now the 1 got added in here and it carries over like that. Okay? Now, the next thing is we take v exclusive over x, right? V exclusive over x. So what is so something has changed here. 1, 1, 1. Right? Now we divide by u. That shifts it over. U is just a power 2. So this is a strange way of normalizing the thing, bringing those 3 ones all to the right. By the way, I have to put parentheses around this whole business. And so now I add that to v. And what? Oh, I got to shift right. I got to shift right by 2. Right. So now I shift right by 2, and I only got 1 left. Now I add v plus, and I'm getting 1, 0, 1, 1, 1, 0, 0, 0, 1. All right. So that's y. Now, notice that y has 5 1-bits in it, and x has 5 1-bits in it. Well, it turns out this is the smallest number bigger than x that has 5 1-bits in it. So now set x to this, do it again. You'll shift this 1 over one place to the left, and so on. You'll run through all the integers that have exactly 5 1-bits. If you start out with the smallest one, which is 31. Okay, that's Gosper's hack. Now I introduced as an exercise a sequence of nested parentheses encoded by zeros and ones, and I was able to out Gosper by having even divide by the square root of u in my formula. But anyway, that's this was, as I say, this is an eye opener to know that we could do something like this, and it's just the beginning. It's just the beginning. Okay, now. I guess I can show next. Yeah, let's talk about. Okay, so how do you make this into a technique? And one of the first things is to study how to operate at the right hand of a word, which is what this is. And so, working with these bits, one of the things that we when we start to learn about it, pretty soon people are talking about what we call the ruler function. which is if you have an integer that isn't 0, the ruler function says how many zeros there are at the right, the number of trailing zeros of the thing. And the reason we call it the ruler function is because if you zoom in on, you see how the tick marks on the ruler get like this. You see the ruler function, if you have an odd number, the ruler function is 0. But if you have twice an odd number, the ruler function is 1. And if you have 4 times an odd number, it's 2, and so on. So the length of the tick marks, goes like the ruler function. One of the interesting properties of the ruler function is that the ruler function of x minus y is the ruler function of x exclusive or y, and so on. So we start thinking about the ruler function, which talks about number of trailing ones, number of ones at the right, zeros, trailing zeros at the right. Then there's a corresponding dual function, the lambda function, which is the integer part of binary logarithm of x, which tells you where the leftmost one is in an integer, a positive integer. If a negative integer has so many ones that there is no leftmost, but this is the leftmost one. And it's kind of nice that lambda is for left and ruler is for and rho is for right. Easy to remember these numbers. Okay, so. A lot of the things that we try to do then are based on an understanding of ways to deal with the bits that are at the right and bits that are at the left, and it seems to be a lot harder to work at the left than at the right, because when you're adding stuff together, you got carries propagating to the left, but we don't have anything that propagates to the right in the same way. And a lot of the basic theory of this subject is still filled with open questions. But and so, for example, I can't prove to you that there is no efficient way to extract the leftmost bit the way I extracted the rightmost bit. Remember, the x and minus x is the rightmost bit. Well, 0. I have no proof that there isn't that tomorrow somebody isn't going to come up with a sequence of 12 steps that is going to give me the leftmost bit. I just haven't been able to think of it, but I haven't been able to think of a way to prove that that's impossible. I do have some lower bounds saying if I'm going to compute the number of zeros, if I'm going to compute the position of this number, to actually compute the logarithm, the lambda x, then I know it's difficult to a certain point. And if I have n-bit words, I know it takes log n steps to do that. But to compute to compute 2 to the power lambda x might be simple. I know of no reason why it's impossible, but I strongly doubt it. Okay, so those are the lambda and rho functions. But there's a great trick which I realized must be true earlier this year, and I told my friend Bill Lynch about it, and I said, it seems to be difficult to compute lambda x, but if you're given x and y, 2 different numbers, and you want to know whether lambda x equals lambda y, that's easy. I don't know how to calculate lambda x fast. I don't know how to calculate lambda y fast, but but I know how to calculate whether one is easy. So I met my former colleague Bill Lynch at a party earlier this year, and I told him, I just discovered that it's easy to do this today. And give it to him as a puzzle, and he sends back by email a solution that was much better than mine. And so Bill said this is true if and only if x exclusive of y is less than or equal x and y. So anyway, think about it. If they have the same leading bit position, then I take the exclusive or that zeroes out that bit position, but the and still has the 1 in that bit position, and the converse also works as well. Okay, so we can test fast whether this is true. Now, another similar thing, my friend Tom Rokicki came up with a similar idea, but related, and that is, I won't talk much about the reversal, but another thing that people always try to do with their bitwise operators is to try to flip a number left to right. Now here it's not an infinite precision integer, but maybe we have a 64-bit integer, so we want to take the bits, A, B, C, D, and so on, and flip them around so that the A is at the right and the B is and B is going the other direction. Tom Rokicki, let me find that page here, exercise 42. That's x, to find out whether the reversal of x is less than the reversal of y is something you can do quickly without testing, without reversing x or reversing y. And the reason, and what you do is you set d equals x minus y and y minus x, and then you test d and y equals d. So, x minus y and y minus x. Now this is remember this is some quantity and it's negative, and so this is the least bit of x minus y. This is the rightmost one bit of x minus y, and so if that happens to be, that's a place where y is 1 and x is 0. And so if it happens that we intersect that bit with y and we haven't zeroed it out, then it must be that y has a 1 in that bit. So when x and y are reversed, you see they'll have other bits that cancel out to the right. So anyway, this is another surprising fact, that without reversing numbers, I can tell what would have happened if I compared the two. And Rokicki found a great use for this, because he lets x and y be the address of nodes in a binary search tree, and this is kind of a randomization which helps him keep the binary search tree balanced. And he said that this improved the speed of a program at Hewlett-Packard by several orders of magnitude when he put this extra couple of lines of so anyway, this is another quick story. Okay, now let's. But I want to get to some more mind-blowing stuff. So go next. One idea that is too cool to omit is this one. The next few things I'm going to be talking about is where we're working on individual bytes. So imagine that I've got a 64-bit word and it's divided into 8 bytes. Or in general, imagine that you have some wide word and it's divided into a small number of fields, or a smaller number of fields, and those fields we want to sort of work on all of those fields simultaneously. But the individual fields aren't supposed to mess up the other ones. So the next trick I want to show you is due to Hank Dietz, and it's to take the average of corresponding bytes. So I have a word x that has, say, 8 bytes, x1, x2, up to x8 in a 64-bit word, and y is y1, y2, y8, and I want to get z, which z1 through z8, where zj is equal to the average of xj plus yj over 2. Like to average these guys out. Yeah. So of course I want to do something like addition. Here's Dietz's formula. First of all, I set z to x exclusive over y, and L bar, I'll explain this in a minute, and shift right 1, and then I take x and y and add it to that guy. So let's call this t instead, so that's not to confuse the issue. So I compute a temporary number which is exclusive OR, ANDed with the with this L bar and shifted right one. I'll tell you what L is, and L is actually 1, 1, 1, 1, 1. It's a 1. It's a 1 at the right position, at the right of every byte. It's simply a low bit. There's 8 of them though. 1, 2, 3, 4, 5, 6, 7, 8. Right? So L is a low bit there, and so what's happened here? I exclusive ORed X and Y, and then I ANDed with saying that you don't have the low bit on. So that means I'm zeroing out the low bit, so that when I shift it right 1, it's not going to go into the wrong field. So that's easy enough. So what I've done is I've exclusive ORed these guys and shifted them right 1. Well, then I AND it and add that to T. And it's just another way of writing the well-known formula that to add two binary numbers, you get it is X exclusive OR Y plus the carries, and the carries are X and Y shifted left 1. I mean, if you're adding two binary numbers together, you take the exclusive OR, and you also have to add in the carries. This is a plus sign too. But now we're dividing by 2, so really I wanted to shift. I wanted to shift this right by 1 and not shift this by 1. So that's what I've got here. So I mean, take the floor by shifting right 1. So that's but it's a formula that is so simple once you've seen it. But you say, why didn't I think of that? Okay. Okay, but more often, I think we want to when we have a lot of bytes. We're doing something where we want to say search through a whole bunch of bytes and quickly decide whether or not one of the bytes is 0. For example, I think you all know the way programming languages like C and I'm sure Java keep track of strings. They store characters and then put a 0, a null character at the end, and that instead of saying somewhere else how long the string is, they just say, no, here's where the string starts, and it ends at the first 0, wherever that happens to be. Okay, so let's imagine that we want to figure out what the length of a string is, and of course it's obvious. We look at the first character. Is it 0? No. Go on the second character, third character until we find a 0. But well, this is taking a few instructions for every character. It'd be nice if we could sort of just glance at 8 characters at once. Let's say we have a 64-bit machine, and say, is there any zeros in here? If not, go on to the next. Okay. Well, here's I used to think it took 4. It took 4 or 5 instructions to do that. You can do it with 3. So X is equal to 8 bytes, and I want to see if any of these is 0. And what you do is you compute H and X minus L and X bar. 1, 2, 3 up. Now H is I'll write it in octal notation. It's 80, 80, 80, 80. It's a 1 in the high bit position of every field, and L is hexadecimal 01. I write this for hexadecimal instead of the OX that C that language does. Okay, so in other words, H has a 1 bit at the top of every byte, and L has a 1 bit at the bottom of every byte. And let's see what happens here. Well, if there aren't any zeros in the word, I claim that we're going to get 0 here. So every one of these bytes is non-zero, let's suppose. Okay. So what's happening then? Well, I subtract 1. I subtract 1 from that byte. I get X minus L, and I've lost. I haven't borrowed into anywhere else. I had some non-zero number. I subtracted 1 from it. It's still 0 or positive, right? Then I look at, I AND it with the complement of this number. So that means that I have to have a bit that was 0 before subtracting 1, but 1 after subtracting 1. I'm sorry. It has to have a 1 after subtracting 1 because I'm ANDing. So I have to have a 1 from this, and I have to have a 1 from this, which meant a 0 originally. So I've had a bit that went that was 0, but after I subtracted 1 went to a 1. Right? But it also so how can that be? You know, if I had a number like x is 10101110, and I subtract 1, and I get 10101001, you know, and right, 1011, good, thank you, and so I would, you know, so this is x minus 1, or x minus L in our field, and then I have x bar is of course 01010011. And so I'm sitting here with 1 1 0 0 0 0 0 0. Now I'm ANDing this with h, which means that these ones have to go all the way to the left. It can't happen. So I'm getting 0. So you know, I'm getting 0 if all of these guys are non-zero. But if at least one is 0, let's take the one that occurs most closest to the right and take a look at it. You find out that you get a 1 bit there. I mean, let's check it out. You got a 0 there, so then you got so it's all zeros. So I subtracted 1, so I got all the ones there, and it was enough to do it. Now, so just 3 operations to give a test. You know, instead of operations loading. Now, exactly leftmost 0 is. So this is the first example I know actually where to like a little Indian storing way of storing strings the way I mean I never understood why Intel did it the way they do, but in this case I can find the rightmost byte by looking at this number, but if I have to get the leftmost byte I have to compute another quantity with 4 instructions that will tell me what the leftmost byte is. So I don't want to dwell on this too long, but anyway. Here's my point is that real quick we can look at 8 bytes at a time. Also, maybe we're not searching for. You have a question?
Are you assuming that you can get the complement of x without the instructions?
And yeah, I'm assuming that my hardware does allows me to do and not in one instruction. Now this is not true on all machines, unfortunately. But you know, next, you know, it soon will be. I mean, as soon as people know these tricks, they're not going to build these stupid machines right now. Right now, in order to get and not on an Intel machine, you have to put it into a floating point register and use the, you know, and you have to set some flags and things like this. It's ridiculous. But you know, on a decent computer. Which you know, like the PowerPC or something. You know. So you know, MIPS, whatever. You know, they should have all of these. My operation counting, assuming you know. Sticking with stupid conventions about the machines that we happen to have right now. I mean, I also, define division correctly instead of the way most computers work. Okay, so now let me give you another example here. Let's suppose, well, maybe we aren't searching for 0. Maybe we want to find the first occurrence of some letter in a long string. You know, we're doing text searching. So you know, looking for the first occurrence of or some character like a $sign. So find the first $sign in this text. All right, well, what you do is you take the word X and you exclusive OR with 8 $signs, and then you look for 0. All right, okay. So now let me give you another example. This one was actually given by Leslie Lamport, who wrote one of the rare articles about this subject. His paper was published, I'm not sure, 76 or something like this, when he worked at Park, maybe, I don't know. Anyway, but he wrote one of the first papers that discussed this kind of thing, but he didn't know that these tricks, such good tricks existed, so he actually took every byte and extended it to 9-bit. But his paper suggested this application, and so here we have, suppose I have x and y, and these are bytes, and then I want z now. In this case, the rule is zj is equal to xj if x and y are equal, but it's equal to an asterisk if they're not equal. Okay, so if they're equal, you could choose either x or y. So for example, you start out with the word like x is beaching and y is belching, then z is beaching. Yeah, okay, that's the problem, is to convert beaching and belching to beaching. Okay. Now, here's the code. T is equal to this h, this high bit thing, ANDed with, and then you take the exclusive OR of x and y, or exclusive OR of x and y and h minus L. Okay, we're not going to go through in detail. You just have to believe me on this one. This gives me something that's ANDed with h, and so so in every byte we're either going to have a leading one or not, and it's going to be a 1 actually if x equals y in that character, and or is it? Yeah, if they're unequal, it's going to give us a 1, and if they're equal, it's going to be a 0. So then I form a mask M by taking t and left shifting at 1 and subtracting t right shifting by 7. This is going to give me a mask that is either all 1s or all 0s in each byte. Then I do this, and it inserts an asterisk where the thing is masked, and it otherwise it doesn't. So that's the solution to this problem. 1, 2, 3. I've already done that with 4, 5, 6, 7, 8, 9, 10, 11 instructions. But it's harder to do. Actually, we did 8 characters with 11 instructions, so it's not too bad. Okay. Now, I got an exercise in here which I had great fun writing, which shows that we can go way beyond this to the following. In 6 operations, suppose I have a number x that has 8 bytes to it, and I'm going to compute 6 operations on x. I'm going to exclusive OR with a constant, and then and call that y. Then I'm going to take y and AND it with b, and plus c, another constant, OR that with y, exclusive OR with d, and AND the whole thing with e. Now I'm supposed to this t is supposed to be a bunch of flags shifted left 7. So in each byte, t is supposed to start out with a 1 or a 0 based on 8 criteria, and each byte is different. I'm actually numbering the bytes 0 to 7 instead of 1 to 8 here. So in the leftmost byte, the rightmost byte here, it's x7 through x1. I'm using this notation now. So, this is base 256 arithmetic. So in the rightmost byte, I'm saying that the flag should be set if the character is exclamation point. The next byte over is supposed to be set if the character is not an asterisk. The next character, if it comes less in ASCII code than a capital A. The next one is if it comes greater in ASCII code than a lowercase z. and here's a greater than or equal to a lowercase a. This one is whether it's the ASCII code for a decimal digit, 0 to 9. And here it's a case where any byte that's less than or equal to 168. And finally, at X7, the flag should be set if and only if it's one of these 4 characters that represents a relation less, equal, greater than, or question mark. So the point is, you can do that operation doing eight different kinds of tests on 8 individual bytes in 6 operations if you just happen to know the magic constants A, B, C, D, and E. Now, why is that true? Well, if I had time, I would explain the answer to you, but you'll have to look. So some of those tests were less than, some were less than or equal, some were in a range, some were unequal tests, but we're doing it all simultaneously. Okay, now when we're doing instructions of this kind, I guess I want to say a couple other things quick. Elwin Berlekamp remarked to me 20, 30 years ago that people are putting more and more gates on a chip. Now you were getting n logic flip-flops on a chip, where n keeps getting larger and larger and larger. But only if you look at the chips, only log n of those flip-flops are either flipping or flopping. Hardly anything is actually happening as far as changing the state inside of the chips that we're building now. This is, I'm not talking about a CPU chip, but I'm talking mostly about a memory chip, where almost nothing is there. But these are built, these are large integrated circuits. So not much is happening. It's so different from the human brain, where we got all our cells are somehow working together, and we're not saying, okay, now you go. Of course, there's an obvious source of inefficiency, and hardware designers have been working for years to figure out how we can do something so that we can handle this and get a lot more, make use of all the potential power that's there. So maybe this Platologic computing will have will lead to some advances in this direction, and for this I recommend thinking of it as trying to imagine a brand new kind of computer that has smart. We might think of it as having smart memory, so that we're not doing these operations in registers, but we're just saying to the memory, go ahead and do some logical ands on what you have. Don't send it to me to do the operation. And so I'd like to assume that we might be able to build a machine that the cycle time would be slower than the cycle times we're now asking for, but still the words would be very wide. And so we'd tell the memory, okay, do a large part of your memory now, and do a bitwise exclusive OR of these guys, or even plus, which involves some carry propagation. And we also would want to be able to shift by powers of 2. And now you could combine that with a normal memory and but just have these as different purposes. So this is rather like something that people have studied for a long time called a SIMD computer, which is a parallel machine standing for single instruction, multiple data, where the CPU is giving instructions and then the different parallel units are all operating on these instructions, and so. Last 10 years or so, there's been researchers in various parts of the world that are talking about what they call SWAR computation. This means SIMD within a register. And so they're thinking, yeah, this stuff that we're doing here with belching and so on, that's very much like SIMD, but we're doing it, we're doing it in our program. So we're using a SIMD kind of approach, but within a register. And there's a nice, there's some website, but there's a compiler called the Swarzy compiler, where you can give it some extension to the C language, and it will figure out some rather clever techniques for doing these operations without you having to figure them out. And it'll do some packing and unpacking and clever stuff. I said earlier, though, I think that it's like time for these ideas to go mainstream, and for ordinary programmers not to have to go to a special compiler for this. And I'm hoping that sometime we might even be able to make use of these things with really wide words, not within a register, but in fact within a smart memory. Doing some calculation. In order to finish up, I want to mention then two things. The first one is let's see. Yeah, I think I have time to do part of it. So Von Pratt came up with this in the middle 70s, and showed that you can multiply Boolean matrices extremely fast using such a computer. Now let me explain this on a 64-bit register. So suppose I have some I don't know, I could get a fairly random idea, but I can write down two 4x4 matrices of zeros and ones for whatever you want to put here, and then I can multiply these together. There's two ways to multiply 0-1 matrices. One is the Boolean way, and one is the modulo 2. But anyway, in either case, this would say take the fourth row as 1, 1, 1. This one would say combine the second row and the fourth row. So if we take exclusive OR, this would be 1, 0, 1, 1. But if I took OR, I could take either logical or exclusive OR here, and this says take the first row, and this one says do the bottom three rows. So exclusive OR, the bottom three rows is 0, 0, 1, 0. Okay, so this is matrix multiplication mod 2, for example, but I could also have done. Okay, now I'd like to do this quickly with a 64-bit register. So let's suppose that I have my 64-bit register, and I got 3/4 of it are 0, and here I put the matrix. So I have 0, 0, 0, 1, 0, 1, 0, 1, and so on. Down here that's x, and then this is x, and then y, and y will be a 16-bit thing like this as well. And I'd like to up to and get z in the same format with a fairly small number of instructions. Okay. Well, so let's suppose that this is A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P times A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P equals, and then I'm not going to write out the whole thing, but as A, B plus B, B, this is exclusive OR, plus B, E plus C, I plus D, M, and the other 15 entries are similar. So matrix multiplication that is starting out with A, B, C, D, E, F, G, H, I, J, K, or up to P, and A through P. Let's on it. Here's the solution. First off, we say x is set to x, or x left shift 16, and then then after doing that, I also shift left 32. So the first time I take this and I shift left 16, and so I get 2 copies of it. And I take this and I shift it 32, and I get 2 copies. So since I have now built a register that goes A through P, A through P, A through P, A through P, 4 times. Same thing for Y. So I've got I've got my matrices replicated 4 times. The next thing I want to do is swapping bits that are 15 apart. And I'm going to change X so that I get AA, CC, EE, so on, OO, and then it's going to have BB, DD, and end with PP, and then start AA, CC, EE, and so on, like this. So these are 32 bits and 32 more bits in X. And how do I get from here to here? Well, I have to swap this A with this B, and I have to swap this C with this B. And so I'm sorry, not that guy. I want to swap the D with this guy. So some pairs of elements that are 15 apart, I want to swap. You can do that by taking X exclusive or X right shift 15. That shifts everything right 15. And then you AND with some mask, which has a 1 bit at the right position of the guy you want to flip, and then you can say X is set to X exclusive or T exclusive or T left shift. Sorry, what is it? X is 13. Is X, yeah, X is X, T, left shift 15. This puts, after I've masked it off, in this position I'll have A exclusive or B. In this position I'll have C exclusive or D. And I'll have zeros elsewhere. Then I take that number and I shift it left 15, and so what I'm doing is I'm changing the B to an A here, and this A to a B here, because I'm exclusive. I'm taking A exclusive or B and adding it to, or XORing it to B, and that changes. I mean, B with A plus B is A, and A with A plus B is B. So anyway, this is what 1, 2, 3, 4, 5, 6 operations, swaps. Guys that are 15 apart, the ones that I want. I choose this, okay, and then I can choose. I can do it again with things that are 30 apart, and I can get A, E, and so like this with another swap. So I can arrange things so that I'm sitting here with X equals A, E, and it's going to end up. I'm going to have each of the. I'm going to have the columns A, E, I, M, and then B, F, J, M, and end with D, H, L, P. It's going to have P, 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 P on the right. With a similar pattern, but instead of using 15 and 30, you use 12 and 24. It turns out you can get Y equals A, B, C, D, A, B, C, D, A, B, C, D, A, B, C, D, and then you can go E, F, G, H, E, F, G, H, E, F, G, H, E, F, G, H, and so on, and ending up with M, N, O, P. But these are caps. Cap A, B, C, D. So these are the elements of Y, but with a little bit of shifting and exclusive ORing, masking, I can get the first row repeated 4 times, and then the second row repeated 4 times, and ending up with MNOP, the last row, repeated 4 times. Now I compute X and Y, and I'm doing simultaneously 64 AND operations. So here I'm getting AA, and then I'm getting AB and AC, and so on, all the way up to PP. And now I look at this, and it turns out that all I have to do is take these 4 16-bit things and I take these 32 and I exclusive OR to these 32, and then I take these and exclusive OR to these, and I've got the matrix product. So I had to go through fast, but the point is that I've used, if I have 2 to the D by 2 to the D matrices, I do 18D plus 2 bitwise operations, and I've got the product. So usually, you talk about time for matrix multiplication. N by n matrix is n cubed. This is log n with a fairly small constant of proportionality. So if you let me take D equals 6. So there's 64 by 64 matrices. So that's 2 to the 12. That's 4,000 some bits altogether. And in the other matrix, there's another 4,000. So I've got 8,000 bits in these matrices. I'm doing 6 times 18 for 110 operations. I'm on these 8,000 bits. With 110 operations, that's only 1/80th as many bits as there are bits. I multiplied these matrices together. Now, how big was my register? My register is 2 to the D cubed. So I'm actually sitting here with an 18-bit, 2 to the 18th bits register. So I'm sitting here with rather wide words. These are 256 kilobytes. But a smart memory could do this, and it's very, and with the low cycle time, and so you could, and they also showed many other operations. Pratt and Stockmeyer showed that many other operations could be done efficiently with this kind of organization. All right. So the last example. Well, what should I go through it or not? I promised to say something about this lambda function, and so I think I can do it. But if you want to leave, go ahead, because I know that it's I've already spoken for an hour and 10 minutes. So here's the idea. Suppose I want to calculate lambda of x. This is I want to know where's the leading one of x. Remember, I told you this seemed to be a tough problem. And let me assume that x is only 16 bits long. I can reduce the 64-bit problem to a 16-bit problem with a couple, by looking at the 4 parts of the words. So now I've got a little bit of breathing room if I have a 16-bit number, and so x is a 16-bit number, and let's suppose x, for example, is 0001, and then 12 other bits that I don't know what they are. Now I'm going to make 4 copies of this number x. So I got 0001 here, and anyway, I'll call it alpha, and I have alpha, 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 and now I'm going to form another magic constant here, and the constant looks like this. The first part, I'll write it in I'll write it in binary: 1, 1, 1, 1, 8 ones and 8 zeros. And then the next one has 4 ones, 4 zeros, 4 ones, 4 zeros, and then 2 ones, 2 zeros, and so on over and over again. I'm getting tired of this. And then 1, 1, 0, 1, 0, 1, 0, 1, 0. Okay, so in hexadecimal it's F, F, 0, 0, F, 0, F, 0, C, 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 and A, is this constant here. And so I'm going to, this is my magic constant, M for magic, and then so this is X replicated, and so now I say Y is equal to X and M. So y is going to have 4 parts to it: y0, y1, y2, y3. Y0 is going to x. Let's say start out with three zeros and a 1. So it's going to repeat. It's going to start out looking like 3 zeros and a 1, and it's going to have 4 unknowns, and it's going to have 8 zeros. This is y0. y1 is going to start out 0, 0, 0, 1, and then 4 zeros, and then 4 unknowns and 4 zeros. And y2 is going to be 0, 0, 0, 0, and then 2 unknowns, 2 zeros, 2 unknowns, 2 zeros, 2 unknowns, 2 zeros. And y3 is going to start out with 4 zeros, and it's going to be like this. So I'm getting some crazy number by taking this x here, ending it with this strange mask, which happens to be truth tables of different projection functions. Well, now the basic idea is, because I showed you that there's an easy way to test lambda x equals lambda y. That was, remember, that was if and only if x. If you take the XOR, it's less than or equal to the logical AND, to the bitwise AND. And so now I've also got these techniques that were introduced by Lamport, which allow us to check whether one byte is less than another byte, corresponding fields. And so what I can do is simultaneously test to see whether if I throw out numbers whose lambda has a 1 and it's 8. Lambda is a binary number, and it's got 4 bits to it. So if I can calculate whether lambda is even or odd by throwing out all of the odd numbered bits and seeing if I've changed lambda, and I can tell whether lambda x has a 2 in its binary expansion by throwing out all leading bits that are in positions that have 2 in their expansion. So then, if I can test, compare the exclusive OR with the AND of these functions, then I'll know whether the bit was 0 or 1, and that's the point of this exercise. And so I'm throwing out. So by taking this magic constant, I'm actually forming some changing on x. So the bottom line is that I can just show you the formula. I don't want to get my pages out of order, so I'll do it this way. This is page formula 96. Okay, so the magic formula is this. This was my funny m here, and then I take h and I intersect it with y or h minus x exclusive or y, and where h has these high 1 bits in it, and then that gives me the that I needed, and then you can shove those bits to the right and collect them. So it turns out that on a word, this is competitive with the way known to calculate the position of the bit of a number, and it do operations in log n steps. So there's an obvious way to do it in log n, but this is log n, which is very good because log n never exceeds 5. I mean, if n is so big that log n is 6, then we've already exceeded the size of the universe. So it's it's an example again then with that even if we allow our words to get bigger, we can do non-trivial calculations once we understand the technique. So for my last, I just want to show you this. So you can look it up in the paper in 98 here. These are 21 21 logic steps that do a calculation that Mike Pedersen and I came up with this. We were trying to prove that something was going to take log n steps, and we found out we could do it with a constant number of steps. And the problem was that we were taking a look at a binary number, and we wanted to find where it had a 0 followed by r ones in a row. Where r is some given number. So like a 0 followed by 82 ones. And I want to mark all the zeros that have this property that they're followed by 82 or more ones. That problem is equivalent to saying I want x bar and x shifted by 1 and x shifted by 2 and so on up to x shifted by 82. In other words, the number of I want this to be a 0 and I want all these guys to be 1. So to find this pattern, it looks like we're going to calculate this. We would need something like log r steps where we could sort of group these by 2s. But to our amazement, we found that these 21 steps actually, we kept trying to disprove it until we finally had a method that took 60 steps, and then we cut it down to 40, and then we cut it down to 30, and we cut it down to 15, and then it didn't work, and then we had to add a few more. So this is just not, so it's it's just another indication that there's probably more things out there, and it's very hard to prove that you can't do something with these operations are powerful. And I find that I keep running into more cases in my programs where I can use this. So this part is not going to be just about fancy things, but I also study applications to graph theory, to bitmap graphics, and I used it to calculate gaps between primes. I just found out that I set some world records on that in that regard because by using this kind of operations, and I think if everybody would know these things, their programs would get better. So that's what I had to say for today. Thanks for listening. Happy to answer questions.
One question. It seems to me that the naive work for why the ruler function is easy and the lambda function is hard is that you've got this negation operator that does most of the work for you.
Negation operator, yeah.
And I'm wondering if that means that the negation operator is in practice going to be somewhat difficult to implement, or whether there would be some...
So actually, one can, electrical engineers have implemented the negation operator. Now you could imagine a computer where somebody give you a dual negation operator. Numbers carries propagate the other way, carries propagate to the right, and so on. And Mike and I said, well, what if we had such a machine? It turned out, and so we have lower bounds saying that in order to reverse bits, it takes log n steps. That's a nice theorem proved by Milterson and Monroe, so bit reversal is known to be is known to take some extra time. So if we built a machine that also allowed us to do this, then we could do the lambda operation faster, and maybe why not? Maybe we should build a machine that also allows to add vertically instead of horizontally or something like that. Because people know how to build those circuits, and so that might make a lot of other things happen. Now in the MX computer, I threw in instructions that have built-in matrix multiply instruction on 64-bit words, and when you combine that with these other things, the exclusive OR and so on, then all of a sudden you find that you can compute cyclic parity codes faster. You can multiply polynomials, and you can do all kind of other things. So the question is, probably what is the small number of primitives that that will that each have power, but you can keep adding more and more operations. But the this one matrix multiply unified 7 or 8 instructions on the alpha computer, for example, and did more than the alpha computer had. But in order to design this a new kind of a computer, it's going to take a genius. I haven't worked out the problems by any means, but I'm just saying this is food for thought. That why can't we have smart memory maybe doing these things, because the engineers have figured out how to do conventional memories. Maybe it's not going to be that much harder for them to add. Now we got better technology to make the memories do more for us. Question from this side?
Yeah, I was just going to point out that we can also slot the value of 2 variables without using a third variables by only using
XOR.
XOR.
Yeah, that's a beautiful trick. That's well known. You take X to X, XOR Y, Y to X plus XOR Y, X to XOR Y, and this does it. It swaps X and Y. Something what?
Unless they're equal already, then get to 0. Both.
I can't hear.
Unless X and Y are already equal, then they get.
Well, these are the aliasing. No, I'm assuming that I can't do this with A sub I and A sub J. Yeah.
So Jean Vimon and his colleagues back in the 80s built programmable active memories, which would have been able to do a fair amount of this stuff. I'm not sure whether that line of engineering, whether anything came out of it or not. Do you know about it? Is it?
I hadn't heard about it. I mean, I know he started working on RSA chips.
This was probably before the RSA stuff.
Yeah, that was later. Yeah, right. So but I'm referring to Vimon's work. Okay, another thing I'm discussing here is what we call implicit data structures, where instead of having pointer, a lot of times we have data structures that you can compute your way to the other part of the structure instead of needing explicit link, like a heap, where you know that the father of node K is the parent of node K is K shifted right 1, and the children are 2K plus 1 and 2K plus 1, and so I talk about what I call a sideways heap, which is another way of that doesn't seem to be as well known, implicit data structure, and I also have. Had a lot of fun with implicit data structures based on hyperbolic geometry, which are pretty weird. But you can use bitwise operations to find your way around a data structure without so much memory. And this is another important use of this kind of thing. Now VMAC worked on unifying data structures in those days, and so I'm referring to that work of his. But I don't know. But I didn't know of this approach. Of course, if that was done in the early '80s, then they wouldn't have had the ability to build machines anywhere like this that we can do with present-day technology.
Right, and it was implemented with FPGAs. Add-on cards that implemented PAMs with FPGAs. Yeah. Well, I don't see where these techniques are would make tech run any faster, appreciably. So it's not general purpose. There's lots of problems that it solves really well, but I can't say that if I had that I would be able to a lot of these other things that people want fast Fourier transform, they can build a chip that's just good for fast Fourier transform. I've never been any good at figuring out whether stuff is
is commercially useful or has any financial value. I'm also excited by the ideas underlying it and so on. But it seems to me that it has enormous untapped potential that could very well lead to a way to make use of this, of the fact that we need a good way to make smarter memories if we want to use things to their potential. Yeah.
There was a UNIVAC computer in the late 60s.
A what?
There was a UNIVAC computer in the late 60s that had a bit reverse.
UNIVAC with a bit reverse instruction.
Because all the vendors for the Navy were screwing up I/O, and finally Captain Grace Hopper said, "The hell with it. Every driver has a load register, no up or bit reverse, and then output."
I see.
So whether it was a typewriter or printer or whatever, and
I see.
And all these vendors were all messing up Little Indian with Big Indian.
Well, Little Indian, Big Indian, I know is a but swapping all n bits instead of just bytes. I'm not sure if I had.
It was just 8 bits.
Yeah, but the that's done by one instruction on mmix, of course, with the matrix multiply. So, yeah.
When looking at the complexity of these operations, I wonder if it makes sense to distinguish the Boolean operations and plus minus and negation, because on a hardware level they have different complexity, especially if, for example, when mapping these operations to FPGAs, they have also different latencies.
Plus, the fact that carries have to propagate makes addition definitely harder than Boolean operations, for sure. But it's still in the class that they call AC0, which means that the complexity grows polynomially with the logarithm of the size, while multiplication is not. Multiplication is way above that. But it's something that I should state that assuming that I can do add in one cycle time is much more difficult than saying I can do bitwise AND in one cycle time. There are very efficient ways to do carry propagation that don't exist for multiplication. In addition, but they still are much more complex than simple 1 bit at a time. Oh, thanks again.